last lecture. And the day after tomorrow we have the tutorial. So today we have to continue our discussion of the so-called Hubbard model. Let me remind you what the model is about. The Hubbard model starts with the diagonal part of the Hamiltonian, which, if acting alone, would simply give you a band, epsilon of k in the d-dimensional space, so d-dimensional Euclidean space. That would give you the standard cosine spectrum. Which is a direct generalization of the well-known one-dimensional cosine spectrum. But then to this, what we add is the Coulomb repulsion between the electrons with opposite spins sitting on the same lattice side. Of course, the Coulomb interaction spreads at largest distances, but for this specific case and the specificity, the special character of this case is the fact that this band is very, very small. It's very narrow. We are talking about the bands formed by inner electrons on inner shells. Therefore, with the strongly localized orbitals, the most important effect is, of course, the one which starts on a given lattice side. This means that all the rest can be taken into account after you have taken into account this. And just for completeness, we add the chemical potential term, assuming that the band sphering is up to us. When I'm saying up to us, that means up to the value of the chemical potential. So we're working with the grand canonical ensemble when the chemical potential is an independent thermodynamic variable. This is a very important problem. This is a very important model, whose general solution, even in 3 dimensions, is still unknown. Lots of it is known using numerical tools, but an analytical solution in 3 dimensions still is lacking. The model is exactly solvable, it has been solved in 1 dimension. It's a very beautiful solution using the so-called Bethe ansatz. It's a special part of quantum integrability. You can go to CISA, join the people from the statistical mechanics group, and there are people like Calabrese and especially Mussardo, or world experts, and in particular in the quantum integrability field. But we are not after discussing. We are not going to discuss the reasons why in 3 dimensions the problem is not solvable, and why it is solvable and how it is solvable in 1D. Instead, we will consider some general features, general properties of this model. And we'll start again with the most transparent symmetry of this model, which is translational symmetry. Of course, every time you make a shift of the lattice side, n by n plus any n, nothing changes. Well, you can assume some periodic boundary conditions, or you can assume instead the model to be, the lattice to be infinite, then translation variance follows immediately. This is fine. Of course, there is one more symmetry. The model remains symmetric if you make a phase transformation of of creation negation fermionic operators, the standard phase transformation, which is global, the same for all the lattice sites and all the states. The Hamiltonian remains invariant. This actually means that the Hamiltonian commutes with the total particle number. And the total particle number operator is just precisely what is written here. The total particle number is a good quantum number. It's concerned. There's nothing dramatic and special about it. Now, what you can do, you can turn to the spin degrees of freedom, and to better understand the structure of the spin degrees of freedom, it will be useful to introduce the spin operators defined at each lattice site. So I fix the location of the lattice site, and here I summing up over alpha and over beta, and sigma is a Pauli matrix. It's a triplet of the Pauli matrices. So this appears to be a vector. In other words, it contains three components, three Pauli matrices, sigma 1, sigma 2, sigma 3, and the same applies to the spin operator. In other words, the spin would be simply 1/2 of sigma, but I put C dagger here and C there, and make a trace over all coinciding indices, just to emphasize that this is not just a spin per se. It's the electronic spin, the spin of the electron, localized at the lattice site. It has an interesting feature. If you recall how the local four-dimensional Fock space is arranged, what are those basis vectors? These are 0, 0. I simply choose the state to be labeled by occupation numbers in the spin up and spin down directions. Here I have 0 here and 0 here, 1, 0, 0, 1, and 1, 1. So the number of electrons here is 2, here is 0, and here is exactly 1. So I can consider this subspace, and then I can leave it to you as an exercise. You can check that in this subspace, the action of the spin operators exactly coincides with the action of the standard spin operation subject to SU2 algebra. So there is no difference between this definition of the spin and the definition of the localized spin 1/2. Suppose I have somewhere in space I have a spin 1/2 without any reference to electrons or fermions or bosons, just spin, just the spin. And I have an algebra of the corresponding components of this this operator. You can check that as long as this subspace is concerned, how should you perceive it? So if you consider all possible matrix elements of this operator in the subspace, these will coincide with the standard matrix elements of the standard spin operator in the corresponding Hilbert space. So here we are talking about Fock space, the Fock space labeled by, whose basis is labeled by the occupation numbers. Right? On the other hand, if you consider the action of the spin operator, of this spin operator, on any of the two spaces, two states, you will get 0. So this subspace of empty and doubly occupied sites appear as vacua for the spin operators, if you wish. which means that this subspace has nothing to do with the spin degrees of freedom. So the basis is arranged in a very smart way. Out of 4 states, 2 of them describe spin degrees of freedom, and the other 2 describe charge degrees of freedom, charge excitation. So this can be shown in a very nice way. Now, well, just you may once you have this definition, you may ask yourself, what is, for instance, the z projection of the spin? It's very simple, because you take sigma z, and for sigma z you get ni up minus ni down. Is it clear what I wrote here? I'm saying that this follows from this. I take the z component of the spin operator. It's a matrix 1, 0, 0, minus 1. Therefore, it's a diagonal matrix. Therefore, everything is diagonal in terms of occupation numbers. And the up and down enter in the way they should, and they should have minus sign because sigma z is second eigenvalue is minus 1. Right? You can also build up an object which is Si plus, which is Six plus I Si1, and this will be without any 1/2. It will be a Ci up, C dagger, Ci down, and correspondingly this will look like Ci down, Ci. This is how the spin operators, the fermionic spin operators, look like in terms of the second quantized operators. It's important to use in calculations. Well, now what you can do, you can build up the total spin operator, sum from 1 to ns, and take any of these 3 components, which it's a vector having 3 components. What you immediately find out, not immediately, it takes some effort, that the total Hamiltonian commutes to the total spin. The total spin of the system is conserved as well, together with, along with the total particle. If I look at the object, U, and up and down, I fixed I don't write it, which is U, C up dagger, C up, C down dagger, C up. How would you prove that this expression is SU2 invariant? By SU2 invariance, I mean the following thing. So I take a C alpha operator, alpha being spin projection, and then transform it to C alpha prime, which is U, alpha beta, C beta, where U is a unitary transformation, unitary matrix with a determinant equal to 1. This is exactly what is meant by SU2. So suppose I do this. The claim is that the total Hamiltonian is invariant. The invariance of this term is trivial. It's a trace over spin variables, C dagger C. The invariance of this term is trivial as well, in spite of being off diagonal I and J. It's again a trace over spin variables. So therefore it should be invariant. What about this one? How can we anticipate the spin rotational invariance of this term? Because very often you can hear, look, this is spin up and this is spin down. Up and down are projections on a given quantization axis. So therefore you have chosen the axis, and the only symmetry which is left is Z2, is the discrete symmetry, changing up to down, and at most rotations in the basal plane, which is U1. What about SU2? SU2 means rotations about any axis. How can you prove it? And why it turns out that such a structure must be SU2 invariant prior to any calculations. I would like you to develop this intuition. How do you think? Do you have any educated guesses, ideas? How would you prove it? Suppose I've chosen the quantization axis, and I want to write down an interaction term, which means that it's a structure of the second order in the creation annihilation operators. Two creation operators, two annihilation operators. This is exactly how interaction should look like. Right? How should I organize? How should I organize my interaction such that it remains local? I'm not moving to some other lattice sites. And yeah, and it's written according to all the rules apply to Fermionic degrees of freedom. For instance, respecting the Pauli principle. I cannot put C up dagger C up times C up dagger C up. It's meaningless because it's nothing but the n up squared, and n up squared is the same as n. It's a first order term. So the second order term requires that the spins are infinite. But if you have chosen already a quantization axis and started quantizing the spins like this, and you roll this n up, and you need another n down, what else would you like to write down except for n down? Once you have chosen the quantization axis, this is inevitable. But who told you that you should have chosen the z-axis? You could have chosen an x-axis and call it z prime, and the result will be just the same. This is kind of pedestrian proof. To do it on a more significant level, what you should do, you should prove that if you build up such an object, which is apparently a SU2 invariant, it's a square of the speed. And you understand what is going on here, right? You should squeeze out from this expression and this representation the Hubbard interaction term. This is not the only way to do the job. There is another way. Another way, even more spectacular. It's much simpler and more spectacular. Consider the object n up plus n down and take a square. Why do I take this? Because n up plus n down is the sum over sigma n sigma, and is nothing but sum over sigma c dagger sigma c dagger, and this is of course is SU2 invariant. Why? Because it's a trace. It does not depend on the choice of the quantization axis. On the other hand, if I take a square of this, the square of the occupation number, the Fermionic occupation number, is the same occupation number. So it gives me an up. The second square gives me down. And here I have twice n up and n down. So therefore, n up, n down is 1/2. N up plus n down squared minus n up plus n down. This is an SU2 invariant, and this is an SU2 invariant. Therefore, this is an SU2. Full stop. Right. A very similar thing you'll get if you consider in the same spirit this expression. Just play a game a little bit. to fill it. This is important. You have to understand that the way you choose the axis, the quantization axis, is absolutely up to your will. There is no preferred direction. If I had applied the magnetic field, then of course the magnetic field would specify the z direction. It will be its own direction. But the magnetic field does break SU2. So there would be no question. Of course, there would be no SU2. But you could have done choose the magnetic field. This philosophy very similar to what we use in theory of phase transitions and in theory of broken symmetry effects. Choose the magnetic field, switch on the magnetic field, polarize the electrons along this direction if you wish. Right? Lower the symmetry. Find out what are the projections, what are the symmetries, Z symmetry up to down, and also the rotations and the basal plane, and then remove the field. This will remain. But at the same time, the symmetry SU2 will be recovered. So this is a trick we always use in theoretical physics when we want to explain the independence on the choice of the quantization axis. All right, we switch on the field, we switch it off afterward. Okay, yeah, now we are coming to a fundamentally important issue. This is, you can hardly find any subfield in condensed matter physics when the so-called particle-hole symmetry wouldn't play an important role. In quantum field theory, this is known as charge conjugation. When you go from particle to antiparticles, it's nearly the same. If you have an operator Cj sigma, which is the annihilation operator, a particle hole transformation would be to replace this. Let me put n here, and let n be a vector. In other words, let n belong to a lattice with dimension d. And I would like to bring this to a correspondence with another, let it be b, and sigma dagger, if you wish. Another fermionic operator, but this is an annihilation operator. And this is a creation. And to keep the discussion as general as possible, let me put the eta in of n here as an arbitrary phase factor whose modulus is 1. In other words, it has the form exponent I gamma of n, where gamma is some phase, local phase, generally speaking, independent phase. So this is what we call particle hole transformation, PH transformation. We would like to know. So what this transformation does. First of all, you build up the occupation number operator and sigma, which is C and sigma. Gamma C and sigma. And this transforms to modulus gamma squared is 1. Therefore, it transforms to B and sigma, B dagger and sigma. And due to the Fermi algebra, this is the same as 1 minus B and sigma, B dagger, B and sigma. So if I call this n, this turns out to be 1 over nu n prime. So basically, it's a transformation n to 1 minus. Occupied means here empty. Empty here means occupied here. This is the meaning of particle hole symmetry. I replace a particle by a hole. Right? Is it clear? I think it should be clear. Now the question is, given this transformation, under what circumstances the Hamiltonian is invariant? Is it particle mode invariant or not? Now we'll realize why we put this eta here. Let us first of all check the kinetic energy. We have a sum over n nearest neighbors. We all have also an extra sum over sigma. I don't write this minus t, I don't want it. Okay, let it be minus t, all right, let it be. And we put this expression, it should be eta n conjugate, eta m, and here I have b m sigma, b m sigma dagger. Right? This is how the kinetic energy transforms, this kinetic energy, under this transformation. All right? But now I can interchange those two operators, since the n and m sides are neighboring sides. It means that different sides, right? I can interchange, but that will cost me changing the sign of the whole expression. Plus t sum over the same n, exponent I, gamma m minus gamma m, bm sigma, dagger, bn sigma, and then after all I can interchange n and m as well if you wish, even though it is not necessary, but I can do it. So, everything is fine except for one circumstance. The sign is wrong. Right? This is fine, but the sign is wrong, definitely wrong. So, it would be all right if I had said that for any neighboring sides ij, any, okay, jk. Okay, let it be nm as it was. For any pair of neighboring sides, the exponent I, gamma m minus gamma m, should be equal to minus. In other words, the phase must know that every time I move from a given side to a neighboring one, I changed the overall phase from plus to minus, and vice versa. Now, what you need to do here is a very simple analysis. And this very simple analysis will tell you the following. There is one choice which is obvious and which immediately satisfies the required condition. You consider the hypercubic lattice. This is a very important requirement. That the lattice which is defined is not an arbitrary one. If you had considered an arbitrary lattice, then you would hardly find any choice for these gammas, for these phase factors which would satisfy this condition. But for the lattice, which is a bipartite lattice, which is divisible into sublattices, like a hypercubic lattice, this is possible. And then, say for a square lattice, I can distinguish between A sublattice and B sublattice. For instance, here I have A, here I have B, A, B, and so forth and so forth. So if n vector belongs to A sublattice, then n plus G, when G is plus minus A1, plus minus A2, and so forth, plus minus AB, then n plus d will necessarily belong to B and vice versa. It belongs to B, this will belong to A. Clear? I think it should be clear. Then, what you need to do is to make a statement. This is I, Q times N. When Q is I by A naught, I by A naught, I by A, which is I by N1, N1 plus N2, so forth, plus N2. What is this exponent? This exponent tells you just precisely what I said. If the sum of this integer is even, then the side n belongs to the same sublattice as the side 0. But if it is odd, it belongs to a different sublattice. In other words, this exponent takes values 1 if n belongs to A, and -1 if n belongs to B. And since these two sides necessarily belong to different sublattices, because they are nearest neighbors, their product is equal to -1. +1 minus times -1. And the sign recovered. In this way, you prove that transformation, okay, let it be as it is, with this choice, keeps the kinetic energy invariant. Keeps the kinetic energy invariant. You may ask, what happens in momentum space? It's a good question. In momentum space, what happens is the following: Ck sigma transforms to Ck plus Q large sigma W. Why it is so? This transformation from particle to whole or vice versa, C to C diagram, is here. But you also have to change the momentum. Why? Because you put the extra oscillating factor in front. And the oscillating factor in front selects from the K space only one vector, which adds to the Fourier transformation exponent Ekn. So all in all, K is replaced by K plus K. We've done it before, so it's in the problem of electrons, fermions, and diatomic rings. The model of the circle. So that's fine. Right. Yes, but this is not enough. And how to see it? In momentum representation, the kinetic energy looks as follows. It's sum over K, sum over sigma, epsilon of K, Ck sigma. When epsilon of K, I think I have written it already. Yeah, that's this one. Now, this is the definition of your Q vector. Your Q vector is this one. And your spectrum is this one. And then you immediately realize that you have a property, a fundamentally important property, epsilon K plus Q is equal to minus epsilon of K. Because each cosine is shifted by half a period by pi, cosine x plus pi is minus cosine of x. And the vector Q, therefore, has a special meaning in the theory of Fermi surfaces of solids, and it's called the perfect nesting vector. There are certain Fermi surfaces which have this property, this partial. Now it's clear what happens if you make this transformation, you get this k plus q, epsilon of k. Here I will have ck sigma negative, I'm sorry, ck plus q, sigma ck plus q nugget. Instead of this, I will write down 1 minus what I want. So we'll have a term of 1 times this epsilon of k and sum over all k. Apparently this sum is 0, because the summation goes over the Brillouin zone, and over the Brillouin zone the cosine has the region when it is positive as well as the region when it is negative, and the two regions cancel each other. So what remains is only this minus piece. So you get minus sum over k sigma epsilon k, and this expression k plus q sigma k plus q. And what you do, the last thing you do is you make a shift k plus q. Plus or minus doesn't matter, because the state q and state minus q is the same state. These 2 points are blue, topology. So therefore I remove this, and because of that property, I recover the original. So I gave you, actually I just gave you the second proof. The first was when you do everything in real space. The second is just the same understanding in momentum space. In momentum space again, what you need to do, you make a shift in momentum space by q vector. But it is just the property of the spectrum that the energy at this point changes itself. You go from a Fermi surface particle-like to a Fermi surface hole-like. You can sit down and work out, especially if it's quite transparent and interesting in 2 dimensions, not in 1, 2 dimensions. So what about this U and chemical potential? So, well, the thing is that for both terms depend only on the occupation number operators, and for the occupation number operators, I have the rule that Ni sigma goes to 1 minus Ni sigma. All those factors, phase factors, cancel because C dagger C is invariant on the phase transformation. So therefore, we simply replace by a particle by hole in a very straightforward way. So what we have is the following: is sum over I, 1 minus Ni up, 1 minus Ni down, and minus the chemical potential, sum over I, and sigma, 1 minus Ni sigma. Okay, so what we have here? Here we have the first term give us the total number of lattice sites. The product, the next product give us the total particle electron number, that's right. And the third gives us plus sum over I, Ni up, Ni up, down. Now this term gives us minus twice mu, the number of lattice sites, plus the chemical potential times the electron number operators. So let us collect the terms. So we have U minus twice mu times the total number of lattice sites. I've lost. Oh no, it's all right. It's all right. plus mu minus u times the total particle number. And plus u sum over I, and this is the remaining term. So we see that the energetics of the two models becomes precisely the same, only in one case, namely when the chemical potential is u divided by 2. Then this term is absent. This term is equal to minus u divided by 2. And this term is also minus u divided by 2. And the interaction part and the chemical potential part transform to itself. So it is only for this specific value of the chemical potential when the particle-hole symmetry holds. Now, if interaction is absent, the point, the value of the chemical potential with the particle-hole symmetry persists is, of course, mu equal to 0, which we know very well because we have a band. We have a cosine band, supposing in one dimension. It's the case we have studied so carefully. This is a particle part and this is a whole part. I can overturn it. By the way, it overturns automatically if I continue. If I take into account the periodicity of the spectrum, make a shift in momentum space by 1/2 of the Brigand zone. But I can think in different terms. I simply overturn it, and the physics must be the same. And the symmetry between this and this, between occupied and empty states, only holds for the chemical potential. It's just in between. Every time it is shifted with respect to 0, then this particle-hole symmetry is incomplete or simply absent. So the important conclusion is that the particle-hole symmetry holds. It's highly unexpected, and you can't automatically anticipate this result for a non-zero value of the coupling constant U. And that's exactly the property of the Hubbard model. Maybe I can tell you a few words about the importance of this relation. Even though what I'm going to tell you will not be a complete picture, it will be a partial picture, but I don't know if you had a discussion of the response functions with Professor Kiselov. So you have an electronic system, and you apply an external field, and you study the response of your electron system. And because for instance, if you apply an external potential or apply an external electric field, what happens is a redistribution of the charge. The charge density should react upon this perturbation and somehow redistribute itself. And then you study what is called the linear response. Did you have any discussion of the linear response functions, or you didn't?
Just one.
No. Just did you have a systematic theory of a linear response function? Because the systematic theory of a linear response function needs an introduction into at least a retarded Green's function. If you didn't have any Green's function discussions, neither with me, that I know for sure, maybe with nor with Kiselov, that's fine. And then I will tell you simply a kind of pictorial result, but an important result. Believe me, at some point you have to believe me that in many cases it is very important to understand the stability of a given state of matter when you perturb your sample or some physical system by an external perturbation of a certain symmetry. and would like to see, to observe or measure the response. Right? For instance, very simple example, straightforward. You have a system which consists of magnetic moments or spins, but in general is non-magnetic. Like a Fermi liquid, for instance, a Fermi gas. Electrons do have spins, but at equilibrium, in the absence of the magnetic field, there is no magnetization, and the total speed or total magnetic moment vanishes. And the same applies to ferromagnets if you are above the transition temperature, above the Curie temperature. Then you are in the so-called, the most symmetric phase. But suppose you apply a magnetic field. The magnetic field in the simplest case is a uniform, weak field, but generally it may depend on space, of the coordinate, and generally it may also be time dependent. The only thing is that you care about and should care about that the magnetic field should not distort your system, their ground state significantly. It should operate as a weak perturbation. In other words, there should be a typical scale, different energy scale in your system without the perturbation, and the amplitude of your perturbation must be much, much smaller than that scale. The perturbations caused by the external field must be calculated, sufficient to be calculated in the lowest order perturbation, say in the first order. But then the logic is very simple, that you measure magnetization, M1, and the response, you are accustomed to the fact, should look like this, roughly. This is the external perturbation, this is the response to this perturbation. What is in between is the so-called susceptibility tensor, the magnetic susceptibility tensor. The system doesn't have to be isotropic. For instance, I can apply the magnetic field in X direction and measure the response, the magnetization in Y direction. If the system is anisotropic, it's a possibility. It can be like this. But more than that, this M may be a function of coordinate and time, generally speaking. Then this formula must be modified in the following way. Then it is the integral over space, over time, dr prime, dt prime, just to distinguish between this r and t, which are fixed. Here I have chi alpha beta r minus r prime t minus t prime. And here I have my magnetic field, which is h beta r prime. This is how the above formula gets modified. It's an integral form. It transforms to some kind of integral curve. But what happens experimentally, people do not measure this quantity per se. They measure this quantity's Fourier transform, chi q omega. In other words, I can make a Fourier analysis of the external field. I can single out the most important harmonics of this external field and ask myself, what kind of response can I observe here in the lab by measuring this quantity? And it's coordinate dependent and it's time dependent, and both dependence can be analyzed again in terms of the Fourier analysis. So generally speaking, this quantity, in the most general case, the most simple case, this is not a tensor, it's a unity matrix, just a scalar. This depends on Q, depends on omega. If I set Q equal to 0, that would mean I'm looking at the uniform response on the uniform magnetic field. If I do the same with omega, if I set omega equals 0, that means that the magnetic field, the perturbation is static. If I have both of them 0, that means that the external field is both static and uniform. This is exactly what we mean when we write down m is equal to chi times h. This is just the case when q equals 0 and omega equals 0. But generally speaking, I may have this and that, both of them. It's not both, it's more than two possibilities. And this is an interesting quantity. It tells you how susceptible the system is. For instance, in a paramagnet, you know that the temperature dependence of chi is well defined as the Curie constant divided by the temperature. It's a finite, and for free spins, it follows this behavior. But if you have a ferromagnet, then it turns out that sufficiently close to a transition, when you go from above, you can hit a singularity. The susceptibility, the linear response function, is singular. It has a pole at t equals to tc, which signals that exactly at this particular temperature, even a small magnetic field can polarize the whole system, which means that it is not the effect of the external field, it's the internal correlations which prepare the system to be polarized. So in other words, by making this experiment using the small h, you probe the internal properties of the system which are present already in the absence of the field. You need field as a trigger just to provoke the system to do it, right? So the divergence of the susceptibility always signals the kind of instability. The state you started from, the state with zero magnetization, the paramagnetic state, is unstable, gets unstable at this point. The system undergoes a phase transition into an ordered state. This is the meaning of diverging susceptibility. Now there are examples related to the electron gas. For instance, related to the charge density in this electron gas. So you may ask yourself, if you have some kind of potential, call it phi, as a function of r and t, and then what you measure is the redistribution of your charge, which can be denoted delta r, delta rho. Delta means that there is a rho average, there is an average density, and there is some kind of extra perturbation caused by this external potential. So this plays the role of external field, this plays the role of magnetization in the previous example. And what is in between is the same linear response function chi, which in case of electron gas, this I think you know, or at least you should know. Let me put it like this. Should look like this. This is the Fk minus Fk plus Q divided by omega plus epsilon k minus epsilon k plus Q. Well, if I'm a consistent person, I would say it's a retarded Green's function, therefore I have to be plus I, and imaginary is positive, infinitesimally small quantity. And these are the fermionic distribution functions, which look like, in the standard way, an exponent epsilon k minus chemical potential divided by t plus 1. And this is what is called the Linhart formula. You have added with Kiselov. I know that Misha is all like, I'm sorry, I know that Professor Kiselov always discusses this question. It's a linear response. It's a linear response of your system. Just I cannot tell you anything on top of what I'm saying, because otherwise I would need another couple of hours to derive all this. But suppose I am interested in the special value of momentum Q, which is Q large, that very Q. That very Q, which is pi, 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 and so on. Imagine that the interaction is neglected. I don't care about the interaction, so the chemical potential is taken to be 0. But then I see that f of k is f of epsilon of k. Right? It depends on k only via epsilon, without this mu. And I also know that shifting the energy by Q large, I invert the sign of this energy. So what happens here is omega plus twice epsilon of k. I will be interested in the real part of this function, therefore this imaginary I is irrelevant. And here I have f epsilon of k minus f minus epsilon of k. Correct? Because it would be epsilon k plus q large. But epsilon k plus q large is minus epsilon k. But now we have a well-known formula, well-known relation. And f minus epsilon is 1 minus f epsilon. It's the property of the Fermi distribution function. It has a very simple meaning that the probability to find a particle or a hole must be 1. At least 1 must be found. So, and on the other hand, twice f epsilon minus 1 is the same as the hyperbolic tangent of epsilon divided by 2t, if I'm not mistaken, with a minus sign, but let me put it like this, shut some number which takes care of the signs and all the rest. And now with your permission, what I want to do is to consider a static limit when omega goes to 0. I don't know this. Then, this transforms to the integral d decay 2 pi power of d. I don't need it, in fact. Well, I will write it down nevertheless, but then it's already clear that I don't need it. I get rid of this 2 as well. The good point is that the dependence on the momentum only via the energy. So therefore I can reduce this integral to the integration over energy, the density of states, and the function, which I have. When the density of states is just your integral over d decay 2 pi to the power of d, and the delta function, epsilon minus epsilon of k. Now we're looking at this integral. When epsilon is greater than the temperature, then the tangent is no longer singular at epsilon, because at small, very small epsilon, it's linear with epsilon and cancels this with a factor 1 over t. But on the greater values of epsilon, it reaches the values of the order 1, and you are left with 1 over epsilon. And the smaller the epsilon, the better. The temperature may be even smaller, but the epsilon itself may be small compared to the bandwidth. So therefore, it would not be a big mistake to push this density of states outside the integral and replace it by its value at 0, just at the Fermi surface. In other words, all physics occurs within in the vicinity of the Fermi surface. I'm not interested in the particular dependence of the density of states on energy. I'm interested in its behavior close to the Fermi surface, because everything happens there. Right? This is a nice expression. Well, I have to then cut off this integral by some window. This W must be smaller than the bandwidth, but sufficiently broad and wide, within which I can replace my density of states by its constant value. And then this function is an even function, it will be coefficient 2. I don't care about the coefficients. The integration from 0 to W. What is the answer? Who can anticipate? You have already some experience in doing integrals like this. Who can anticipate, who can guess what kind of integral we are having here? What is this? Ideas? Well,
W over 2T should be good.
The condition is, of course, the temperature is much less than W. And the W is less than, say, T, when T is this hopping voltage. So this derision.
Gives logarithm. It should give logarithm
Logarithm of what?
of W. Logarithm of T divided by
Well, it smells like a logarithm, that's true. 1 over epsilon hints to that, but what to do with this function? What it does? What is its function? Well, you can go to the, again, take a thick book, tables on integrals, and find out the result. And you can do it, integrate this integral by yourself, quite accurate. You can develop a systematic expansion in a small parameter. You can do that. It's a nice integral, very nice. But you can do it exactly in the way I suggested during one of the previous lectures. Look what we have here. We have the integral which has potentially a dangerous point, epsilon equal to 0. And in fact, this point is not dangerous, because at epsilon goes to 0, the hyperbolic tangent goes to 0 as well, and this singularity is cancelled. Right? But then I know that the hyperbolic tangent, which is linear at small epsilon, hyperbolic tangent epsilon divided by 2t, at values of epsilon of the order of t start curving up and saturates at the values of the order 1. That's the property of the hyperbolic tangent. So when epsilon becomes of the order of t, the tangent, hyperbolic tangent, approaches asymptotically to the value of 1. And you are left with 1 over epsilon. So you don't care about the lower limit. In the very low limit, low energy limit, you're fine. You're guaranteed no singularity. But you are cut by what? But which value of the energy? But those values of the energy when the tangent is small. That means that the lowest value of energy, allowed value of energy, should be of the order of t. And then you forget about this, because at the higher values of energies, tangent can be replaced by 1, and you are left with the epsilon divided by epsilon, and the upper limit is w, which is the highest. So you're versus double logarithm double u divided by t. Right? Which tells you what? Which tells you this susceptibility at the specific value of the q at the nesting vector is logarithmically divergent when the temperature goes to 0. This divergence only occurs at 0 temperature in the static limit. Which means that in the static limit, such a system like a, by the way, please notice I never used any dimensionality. I only used, my assumption was the density of states behaves decently close to the Fermi surface. So it's the result is valid for any dimensionality. And follows from the only condition, which is this one. Everything is due to this condition. The nesting condition in any space dimension, if your Fermi surface, because we in some way are discussing now the properties of the Fermi surface, if the Fermi surface is such that this property is obeyed, then this follows immediately. Such a normal state with this property of the one particle spectrum, the normal state, normal ground state, is unstable with respect, for instance, of a spontaneous creation of a charge density wave with a characteristic momentum q. And the characteristic momentum q will tell you that delta rho as a function of n will be proportional to I q n, and will give you a factor -1 to the power of n. And you get for free down the charge density wave already in any dimension. Which means that if you have a lattice, at these points you will have an excess of your density, and at these points you will have a deficit of your density. It will be positive here, negative here, positive and negative. Extra charge will be plus, extra minus, extra plus, extra minus, extra plus. A typical charge density, and the same in the perpendicular direction. If you add a third direction, it will be all the way the same, because you divided your lattice into sublattices. It's a bipartite picture. So this is the manifestation of the importance of the nesting property. We have found the example when the linear response function gives you the logarithm, but essentially this is not the whole story. Let me go further. I will sacrifice the discussion of the Harvard model. You will take my lectures and read for yourself. Or we can discuss it maybe on Friday during the tutorial. The things which I didn't manage to cover today. So this is the polarization. So you have a perturbation. The perturbation has your external magnetic field, external potential phi, which is characterized by frequency, by the momentum q and frequency omega. And then your electron gas start filling this potential, which is inhomogeneous and time dependent. What specifically is influenced by this perturbation is the electron density. Now the electron density as an object is described in terms of the so-called field operators. They're always a function of r. This is psi r. I don't write the spins because the spins are irrelevant. Psi of r. When these field operators are nothing but they can be expanded in terms of plane waves or block waves, essentially in the same way as we do with the wave function. Now, for the wave function, there will be a function, there will be a plane wave, And these will be coefficients whose modulus square will give you a probability of a given statement. In this case, these are just simply operators. This is an annihilation operator of the specific K state, and this annihilation operator in the real space representation. It's a change of representation. Here we work with the real space representation, but in the discrete lattice here we have backward back to the continuum, and we can do this. And now if I do this picture, I can show that, in fact, I can write down the following Fourier expansion for the density. It's a rho of Q exponent IQR, when the rho of Q is sum over K, CK dagger, CK plus Q. But you can also build up a rho of Q dagger, maybe it's even better to do it. CK plus Q, dagger, and CK. Now imagine that I'm acting by this operator under the field Fermi C. The field Fermi C, it's not a vacuum state. The field Fermi C is a state in momentum space Kx, Ky, Kz, which represents a sphere or radius Kf, which is called the Fermi radius, such that all the states inside, I'm talking now, I'm back from lattice to continuum, but it's an ideal Fermi gas when all the states inside are filled and outside are empty. So it's a vacuum only for the holes. There are no holes inside, but it's not vacuum for the particles. So, if I'm acting by this operator onto this field Fermi C, the action of the annihilation operator is only non-zero if K is less than Kf. If K is greater than Kf, if I'm somewhere here, there is no occupancy here, there are no particles here, there is just a vacuum. C acting on the vacuum gives me zero. That's the definition of the vacuum. So CK, I can annihilate any states under the condition that the state is already filled. If it's not filled, it's zero. So this is the state called K. And I kill it, I annihilate it. And then I bring it to a state which is K plus Q. But I have to bring it outside the Fermi surface, because if this state is inside Fermi surface, first of all, the Pauli principle doesn't allow me so, but if it is inside, it's actually on F of. In other words, what is written here? It's a creation of the particle-hole pairs, particles with the momentum K plus Q and the hole with momentum K. Right? Particle with momentum. So the particle-hole pairs described by this combination represent Fourier transforms of the electron density. Fluctuations of the electron density means the creation of the continuum of electron-hole pairs. If I had a longer course as I had in previous years, 16 lectures, 24 lectures, we would have this discussion done in a more systematic way. Right? So what this perturbation does, it creates particle-hole excitations. It creates fluctuations of the density. So therefore, if I denote by this line a creation of a particle with momentum K plus Q, then I have to annihilate this particle, have annihilation of the state K caused by this external perturbation. So this perturbation gives rise to a hole. Looking for a hole, I have to move opposite to the arrow. The hole, according to the great Dirac, is the same electron moving in the opposite time direction. Don't forget it. Keep this in mind. The physics is just the same. So I have a particle-hole pair here. Then this particle-hole pair can recombine at some point, and again create a quantum of this external potential. And this is a typical process which takes place in the lowest order perturbation theory in terms of interacting particles. Here the particles are non-interacting, and therefore what I have calculated here with the logarithm in the answer is nothing but this single polarization loop. This k plus q will give me something like fk plus q. This will give me minus f of k. And in the denominator, that will be the result of integrating over the product of two so-called fermionic propagators of Green's functions. But it's a different subject which we didn't touch at all. So this is the picture for the susceptibility, which we had just calculated. But if the system is interacting, this is not enough. You can put interactions. Let me change the color. You can put them like this. This dotted line, dashed lines are labeled U, since you have two processes, so that your interaction is always of this kind. The elementary interaction is of this kind. It doesn't matter that it is U, just this form. This is the structure. This is the genuine structure of interaction. But this is not the most important one, because you may consider these diagrams, and so forth and so forth. And under certain circumstances, and it is true that this is not necessarily U. It may not be U, it may be anything else. But the idea is, even already with U, you will have these diagrams, along with these ones. If it turns out that for some reasons, you already can see, if I have this bare bubble without any complications, I already have this logarithm, which is divergent at low temperatures. Now, when you have a batch situation, divergency, what should you do if these divergences are multiply and generate more and more divergences? You have to select the most divergent contributions in perturbation theory and try to sum them up. Then from the result of this summation, you may hope to find something which you cannot see in the lowest order. In the simplest case, this is some G proportional to this U, for instance. And the series that you have is something like, let me call L is the log. GL, chi is proportional to L plus GL squared plus G squared L cubed, and so on and so on. If the system looks, if the sequence of these diagrams look like a geometric series, for instance, you can sum them up very easily. And the result will be L 1 minus G. That's a school exercise, high school exercise. Now, what you observe from this, if this is correct, and if it turns out that G is positive, then you remember the ferromagnet? In the ferromagnet, you have 1 over T minus Tc, right? You remember this? Instead of this, your susceptibility now turns out to be proportional to 1 minus G and logarithm W divided by T. If G is negative, nothing dramatic happens. I lower the temperature, and this denominator is never 0. The logarithm increases, the ratio decreases, that's it. Which proves the full stability of the metallic state. Nothing dramatic happens to the originally suggested metallic state. But if this G is negative, then there exists a temperature, Tc, which is of the order of W exponent 1 over G. And such that at T greater than Tc, your chi is positive and finite. It diverges exactly at T equal to Tc and becomes negative below Tc. The susceptibility cannot be negative by definition in this specific instance, which means that it's a signature of full instability. So you have found out that at T equal to Tc, something dramatic should happen to your system. Your system must be unstable with respect. With respect to what? You have been studying perturbations to external potential with Q equal Q large and omega tending to 0. A static external potential which would like to establish a charge density wave with the period determined by Q. The system remains with nothing but accepting these rules of the game. The metal goes in your memory to something past event, good times with the metallic state, and you start your life with the charge density wave. That's more or less how instability occurs in interacting Fermi systems. The problem is that you don't always are so lucky to have a geometric series to sum it up. You are not always lucky to have a simple sequence of diagrams. It's everything I'm telling you. It's already Feynman diagrams, as you can perhaps anticipate. It's quantum field theory already. It's high energy physics already here. There is absolutely a priori no reason to expect that the diagrams with the crossing lines, more complicated, will be less important than this simple and nicely looking geometric series sequence. In that case, the problem becomes extremely complicated and may lead to many, many different results. So the ground state can be in many ways unstable, not only with respect to the charge density wave, but with respect to the spin density wave, with respect to, say, a spin nematic phase or a simple nematic phase, or for instance, a superconducting state, which we never discussed. So let me do the following. Since I started the Hubbard model, it would be highly unfair to stop at the discussion of its symmetries, but at least one important result related to the Hubbard model is the physics of Mott insulators and antiferromagnets. Remains to be discussed. I will do it on Friday, with your permission. I will take some of your questions on the current material, and I will steal from you at least half an hour to discuss what I did manage to do today. Questions? So we are at 11 as usual on Friday. Yeah, and then we'll discuss on Friday perhaps the things related to the exam. All right? Okay, see you.